Thank you.
See
Okay.
you. Good luck.
See you. Hello.
So hello, Hyanga. So we should be live now. So you first requested to play the video, right? Are you going to present live?
I because I have a baby around, but that problem seems to be solved. I can also present live now.
Okay, it's even better then. So let me just introduce the paper, and then you can go ahead.
Okay, thank you.
Thank you. So this is the last paper of our session. So it's called Automatically Assessing and Extending Code Coverage for NPM Packages. And it's a paper from Rian, Andrea, Daniele, and Walter. So you have 30 minutes for the presentation. So please try to leave at least 5 to 10 minutes for the discussion. So the stage is yours.
Okay, hello everyone. My name is Haiyang. I'm from University of Nagano, and today I'm going to present our work about automatically assessing and extending code coverage for NPM packages. And this work is done by me, Andrea Rosa, our professor Walter Pinter from our university, and Daniele Bonete from Oracle Labs. Sorry, I misclicked. And I need to join back.
Yes, I cannot see your screen.
Okay, should be okay now, right? Okay, so this presentation is going to be divided into 4 parts. First, I will cover some background knowledge about Node.js and the package manager called NPM. Then I will share with you the motivation and challenges to have an automatic testing tool for NPM packages. Next, I will introduce our tool named TESA and how it solves the challenges. Finally, I'm going to present the evaluation result we get by running our tool on 500 popular NPM packages. First, let's begin with some background information about Node.js. In case you are not familiar, Node.js is a backend JavaScript runtime that executes JavaScript code outside the web browser. By enabling both the browser and the server applications to be written in JavaScript, Node.js solves the boundary between the browser and the server and gains more and more popularity among developers and the companies in the past years. PayPal, LinkedIn, Netflix, Uber, we have seen more and more applications powered by Node.js, including these big names. One important successful factor that contributes to this is that Node.js uses NPM, a package registry where developers can freely upload their own library to be used by the others. In this slide, I'm showing a figure that shows the number of packages available in NPM in the past few years. We can see that a tremendous growth in the past decade. And currently, there are more than 1.5 million packages in NPM, making it one of the largest packages registry in the world. Here's another figure. Now I'm going to show this is a different another important feature of the NPM ecosystem. This figure here highlights the dependencies among NPM packages. In this figure, a node denotes an NPM package, while an edge represents the dependency from one package to another. And the size of the node reflects how many dependents it has. We can see that it's not uncommon for a package to depend on many other packages. And on the other hand, some popular packages could have many dependent packages, and further forming this complicated, highly coupled graph. So we can see that the benefits of having such a huge package registry is obvious. There are so many packages available for different functionalities. So developers can simply reuse these packages for their work instead of building it on their own. This makes programming very convenient and highly productive. However, such convenience and productivity come at a cost. Applications can be vulnerable to any problem of the package they depend on. For example, in September 2018, a popular NPM package called EventStream is hacked, which was injected with malicious code that steals the user's Bitcoin account. The malicious package had more than 8 million downloads in only 3 months since it was introduced, causing a big loss for applications which were depending on this package. So, given this big background information, next, I would like to share with you the motivation to build TESA, our tool of test automation for NPM. So we know that good tests are very important to ensure code quality, and having a test suite with good code coverage is very fundamental. However, existing studies show that assessing code assessing code coverage of JavaScript projects and packages is a non-trivial job, and many of the packages suffer from no tests or low code coverage. However, there are some limitations of this existing study. First, the study is not scalable, as it was done by manually testing and then measuring the code coverage. In addition, it didn't propose any further solution to increase the found coverage when if the coverage is very low. So here's our proposal. First, we want to automate the process of testing and code coverage, and we introduce a workflow that can fix common test failures. And then secondly, we search tests from different sources, including not only original tests inside the target package, but also dependent tests, which are the tests of third-party packages, depending on the target we want to analyze. So the idea here is very simple. These dependent tests may cover code that is not covered by the original test, so that it can be used to increase the overall code coverage of the test suite. Thirdly, we assemble a test suite from all the tests we find and provide an algorithm to compact the test suite to reduce the size of the test suite. Finally, we integrate a dynamic analysis framework with TESA and supports to run existing dynamic analysis tools on the test suite we find. Now, from this slide, I'm going to show how TESA works. First of all, I'm showing how I'm starting with how the basic testing of NPM package works and why it is not enough. So an NPM package can be tested by simply running npm install and then followed by npm test. We can check the Xcode of the test command, and we can know if the test is successful or not, if the Xcode is 0 or not. However, such basic testing is far from enough. For example, it cannot distinguish empty tests from successful tests, even though both of them will return a 0 code for the Xcode. In addition, some failed tests may be fixable. We may miss the opportunity to include these tests without fixing them first. Now I'm going to show. So there's a famous code coverage measurement tool called NYC for npm packages. However, there are some limitations of this famous tool. And so in ideal cases, you can get code coverage using NYC by simply run NYC npm test. This will generate a coverage report for executed source code. However, NYC doesn't always work because it needs to hook source code noding for code instrumentation, which can be conflicting some other testing harness and some linking tools that would try to auto-format the code. In addition, the NYC tool tries to collect coverage report based on exact source code locations, and is very sensitive to the version of the code. You can have a coverage report for version A and the coverage for version B. These two will be totally different and cannot be comparable. They are not comparable. Finally, NYC by default only measures code coverage of the executed files. So you may see some coverage report with high coverage, but that can be not true because unexecuted files will not be reported by the tool in the default settings. With TESA, we handle these challenges mentioned before and achieve automatic and accurate coverage measurement in the following ways. First, TESA increases testing successful rate by fixing common misconfigurations we identify with our experiments. This part is done manually, but after having these common mistakes, the process can be automatic. TESA also extends the usability of the coverage tool NYC by patching non-conflicting testing harnesses and disabling the other tools that could be causing any conflicts. Finally, TESA also increase the accuracy of coverage reports by using checksums to verify code versions, and also increase and also try to scan all the available source code files to count into the final coverage report so that the result is complete. In more detail, this slide I'm going to show the workflow of how TESA works. First, given a package N and its version V, TESA will first crawl the Node.js project for the package. TESA not only downloads the exact release from the NPM registry, but also try to fetch the closest version of the package's GitHub repository. Then TESA will pre-process the downloaded project to fix common mistakes and the conflicts for the coverage measurement, and then when we testing a GitHub release that have and it's possible that the release have tests, but the version doesn't match the version we are interested in. In this case, TESA have a special algorithm try to patch the code and try to increase the validity of the tests to see if the test can be transplanted from one version to another. Next, the next step, TESA will try to run coverage measurement with our modified NYC. So the modified NYC can produce more consistent results for later processing. Finally, in the result processing step, our tool will check if the test is successful and has non-empty code coverage, and store the results for further processing. So we have mentioned that TESA not only search for tests from the NPM registry, but also from the GitHub repository, which maintains the code. Now I'm going to explain why this is useful and what are the original and dependent tests. So the original tests are the tests we find by applying the workflow on the target on the target package itself. So it can be either from the NPM repository, and it can also be from the GitHub repository. But from our experience, many packages do not ship their tests in their NPM release, so we have to depend on their repository to find the tests. This is our we will show more with our evaluation results. And then we can apply the so we get the original test from the developers, and we can the dependent tests are different from the original tests because they are not from the developers of the target package, but from the other packages that uses the package, the target package. So we basically apply the workflow for the dependent of the target package, and we need some special configuration in the workflow so that the coverage tool will measure the coverage results for the target package instead of the third-party package that uses the target package. There are some details in some engineering details that I'm not going to cover in this slide. In case there are too many dependent packages, we also have some heuristics to rank the candidates by the chance they could produce a very good test. And this, for example, in our current implementation, we rank the packages by daily downloads and prioritize the packages with higher daily downloads. So we have seen showing that we find tests from original package and also from the dependents. However, what if we have too many dependent tests, and all the tests we find can take too long to finish. In order to deal with this situation, we implement a compaction algorithm for the test suite we find, where we try to minimize the time needed to execute the test suite while still maximizing the overall code coverage. The compaction time is a one-time cost. We compute a forehead to produce and we will produce a compacted test suite that can be used that can be directly used for further analysis. And so now one use case of TESA is that we can use the tests we find to run dynamic program analysis. So in order to achieve this, we integrate TESA with a dynamic program analysis framework called Node.js, which is also an open source tool from our group. The Node.js itself allows you to define dynamic analysis and then run it on a Node.js project. And with the integration to TESA, we can easily port any existing DPA dynamic program analysis tools which Node.js supports and run them with the test suite found by us. And with TESA, the dynamic program analysis can be more effective because of the better code coverage. We will cover more with our evaluation result. So till now, I have introduced the background and how TESA is work. And now I want to show some evaluation results we get by running TESA on 500 popular NPM packages. So we do these 500 packages are chosen by there's no standard way to say which package is the most popular. We do this by ranking the packages according to their daily downloads and how many stars of their GitHub repository, and also how many dependent packages they have. And in this figure, I'm trying to show the cumulative distribution of the coverage for if we consider only the original tests we find. With our tool, we collect statement, branch, and function coverage provided by the coverage tool. But I'm going to focus on the statement coverage as an example in this presentation. The x-axis in this figure shows the statement coverage in percentage, while the y-axis is the number of packages. So a point xy in this figure would mean that there are y packages with at least x% statement coverage. So in overall, the higher the curve is, the better coverage that the test suite has. So there are three curves shown here. The NPM curve shows the result if we only consider tests in the NPM registry, which we can see the coverage result is quite low. The GitHub curve shows the results for tests we find from the GitHub repository, and the top line shows the overall coverage if we consider both tests in NPM registry and the tests in GitHub. So we can see that most packages do not contain any tests in the NPM registry. This is somehow expected because they want to reduce their release size, so they actually don't include these test codes. The GitHub curve shows a much better coverage, with 154 packages having at least 80% statement coverage. We can also see that the original tests we find here by combining both NPM and the GitHub tests is still not satisfactory. Only 600 and only 165 packages we found with 80% or more statement coverage, while we were not able to find any tests almost for half of the packages we test. So I'm going to show that how by including the dependent test, how the coverage has been improved. So we can see that there are three curves here. The red one shows the coverage of the test simply from the dependent test, and the the round points highlights the test for the original test, and the cross curve shows if we consider both the original and the dependent tests. We can see that the TESA we are able to find dependent tests for 70% of the packages, which is more than the original test. And the 80% of the packages now have at least some original or dependent tests. The number of packages that have at least 80% statement coverage has also increased by almost 20%. So we can see that by finding the dependent tests, we are able to improve a lot the code coverage for these popular packages. And so I will also briefly talk about some results we get running our compaction algorithm on the test suite. On average, the compaction algorithm can reduce the time needed to finish the whole test suite from an average of 130 seconds to 22 seconds, which means it saves more than 80% of the time needed to execute the test suite while remaining the same code coverage. And finally, I'm going to show some results we get by running some existing dynamic analysis tools supported by Node-proof. We chose two famous ones from the JIT-proof paper, and these two analyses is trying to find some inefficient JavaScript array uses. So compared to only run these tools with the original test, we can find 2.5 times more findings with the dependent tests for the first analysis, and 2.1 times more in the second analysis. So basically, this gives you a high-level view of how the extra coverage we get by including the dependent tests can make dynamic analysis tools more effective. So to summarize, we have implemented a tool called TESA that automates the testing and coverage measurement for NPM packages, which makes it more scalable and compared to existing approaches. TESA can assemble a test suite with both the original tests from the target package and the dependent tests from other packages, which bring more coverage. Finally, TESA is integrated with a dynamic analysis framework called Node-proof, and it can make dynamic analysis tools more effective with the extra coverage we provide. So that's it, and more details can be found in our preprint paper, and I'm happy to take your questions.
So thank you very much for your presentation, Yang. So we have a question here in the chat. So a question from Alejandra. So she congrats you on your work and then asks, how complex is the preprocessing that you do? I wonder how much it influences the whole algorithm. Do you think the preprocessing stage is good enough and finished, or you still need to tweak it to improve your algorithm?
Actually, this is a very, very good question. So there are many engineering efforts behind this work, and currently we are improving it a lot. For sure, it's not finished. There are so many third-party tools that can influence the processing of running the test coverage and collecting the coverage reports. We are only solving. We have been improving the tool by manually checking the error. Unexpected results and fixing commonly seen third-party tools. And this can take a while to cover all the failed cases. And we still need to tweak it more. But currently, it's still in a prototype stage, and we aim to improve it, and so that finally we can make the tool open source.
Mm-hmm. All right, great. So one clarification that was not clear, from your slide. So when you mentioned that you apply the compaction algorithm, that's some sort of a test suite reduction or test suite minimization approach. Do you apply it on the top of the whole test suite, the final one, or you apply it only on the test cases that you crawled from the dependent projects?
It's configurable from engineering point of view, because we can choose which test case we run algorithm, but it's possible to run in either case. But by the default behavior is that we run it for both the original and the dependent tests.
I see. So for the experiments, which configuration you use? The whole test suite or only the dependent ones?
Pardon?
For the experiments that you performed, you applied the compaction.
For that one, I was using both the original and the dependent tests.
I see. So maybe then could be some sort of a risky thing, right? So if I understood it correctly, you have the original test suite that you get from GitHub from the developers, and then you crawl from other projects from the NPM registry to improve coverage. At the point where you have like a test suite that's a combination of the original one plus new test cases, if you apply the compaction algorithm over there, you could risk eliminating some test cases that have been written by the developers. So this would be like removing a test case that was consciously developed to cover some specific area or function by some other test case just for the sake of improving coverage. Could this happen? Could this be a risky thing, having the possibility of using this configuration?
It's a very good point. So actually, the compaction process is the optional process. Because my group, our work is mostly about the dynamic analysis, so we actually tend to run to all the test cases we found. But just in case it's too long, some people don't want to that long, they can take the compaction algorithm, and on their demand, they can choose to run it only on the dependent test. Is also possible.
I see. So another one. So in the paper you discussed the results of Node.js, right? So the experiment was in 500 projects, but there is only one that's deeply discussed and so on. So I was wondering if there was some target projects for which you noticed that even if you crawl new test cases from dependent projects, you were not able to improve coverage, for example, or the improvement was negligible?
Actually, there do have. Some are caused by limitations of the coverage tool. Like they have some problems supporting some new features like modules, and in some specific case settings. And there are also cases where there are just redundant code that is not ever touched. It's possible this code are not. Could be some, because some people can put a specific release version, cleaned and polished, like formatted in the repository. That is not used by any test. It's also like by manually observing the repository. That's a possible case. So in that case, it's one course that could need to. We will not be able to cover that code.
Mm-hmm. So perfect. So let me try to make a quick one because we have about 1 minute. So did you manage to find any new bugs with these, let's say, optimized or augmented test suite that you were not able to capture with the original one?
We wanted, but the time was limited, and we haven't fully use it for further analysis. We were mostly to make sure the tool itself works. So that's why we chose to sophisticated existing tools, but we are trying to apply it for new analysis and try to use the new analysis to find bugs. That is probably for next step.
All right. So thank you very much again for the very nice presentation. It's a really interesting work. And for everybody in the audience, stick with us that we are going to the closing session in about 10 seconds now. So see you soon.
Thank you. Bye.